We've covered a lot of ground in this section. Right now, it may seem confusing, but we'll sort it all out and summarize. The goal was to take those sine and cosine angles, spin them around fast enough until they made tones you could hear, and then compare them to musical instruments playing a single note. It all started with the trig functions you were introduced to in geometry and saw on page 3 of this section of the website. You remember the classic ladder against a wall problem where you were given an angle and a length for the ladder and you had to find how high the ladder would be on the wall? Well, that's where it all begins. Then, we put that angle on a unit circle and look at x and y values of a point. As we spin the angle from 0 through 90 degrees, up to 180 degrees, and then to 207 degrees, and finally back to 360 or 0 degrees, we trace out curves for sine and cosine since, on the unit circle, the x-coordinate is cosine and the y-coordinate is sine. Notice that these plots are of the values of sine and cosine as a function of theta, the angle, as we saw on page 3 of this section of the site. These plots do not have the same concept of frequency, which is how fast we spin around the unit circle. These plots will look the same no matter how fast or slow the vector spins. Since frequency measures how fast we perform a repetitive motion, let's think about how fast we go around the unit circle. I measure about 10 seconds for the spinning vector to repeat its trip all the way around the circle, starting at 0 phase and ending back at 2 pi phase. This means the period is about 10 seconds and the frequency is 1 over the period, or 0.1 hertz. We looked at going around the circle faster and faster on pages 4 and 5 of this section of the site. This value is well below the human hearing range of about 20 hertz. Let's look at putting time on the x-axis instead of just angles so that our sine and cosine curves will show the frequency. We can think of the previous theta angle as being a function of time. We measured a period of about 10 seconds to complete a revolution about the circle. Phase, as a function of time, would be what fraction of that period we have completed right now multiplied by a complete revolution of phase, or 2 pi. The fraction we have completed is current time divided by period. Hey! Wow! We have an equation for angle theta as a function of time. Theta of t is 2 pi times time divided by the period, or, equivalently, 2 pi times the known frequency times time. On page 5 of this section of the site, we calculated 2 pi ft, with t being elapsed time since you hit the start button and f as the frequency you chose. We compared this value to the observed theta by keeping track of how many complete revolutions around the unit circle we had made, and observing where we were on the unit circle. We showed that the observed theta was exactly equal to the calculated theta, and that theta is equal to 2 pi times frequency times time. Now, we can create our sine waves with the concept of time so we can see how fast the vector is spinning around the unit circle. Let's recreate the spinning vector on the unit circle we have been using, but let's use the new time based plot for the sine. The upper two diagrams have a period of about 10 seconds, as you are used to by now. The lower two diagrams of the spinning unit vector and its associated sine wave plot are exactly twice as fast as the upper two. You can measure all this with your timer if you'd like. Notice, when we hit t equals 5 seconds, the lower plot completes its first period, and that is circled below the plot as 5 seconds. The upper sine plot doesn't start to repeat until 10 seconds, indicating a lower frequency. Pages 4 and 5 of this section of the site allow you to create frequencies and calculate the resulting theta angle. Aren't these new sine plots so much more informative? These two frequencies produce tones, but they are well below the human hearing range. When we get up to a frequency we can hear, we will have to give up the unit circle as your computer and your eyes will not be able to spin fast enough. We're going to do that right now, looking at and listening to sine waves you can hear. Remember back on page 2 of this trig section, entitled Trig Functions Make Music, when we presented the C major scale and you created notes out of sine waves? Let's revisit this again and just look at 3 notes: middle C, the C above middle C, and the A in between. I will present each note individually from lowest to highest and lay each waveform onto a common graph so you can compare. We are now playing middle C at approximately 262 Hz with sine waves sent to your speaker. We are showing the plot for this waveform in red. Now, we will play A at 440 Hz in the same way and show the plot in aqua overlaid on the previous plot. You can see how, as the pitch increases from middle C to A, the waveform frequency increases from the red waveform at 262 Hz to the aqua one at 440 Hz. Now, we will listen to sine waves an octave above middle C at approximately 523 Hz and overlay its corresponding waveform in purple over the earlier ones. Now, you can see that this purple waveform has the highest frequency, with over 5 cycles in a 10 millisecond span, while A only had 4 plus cycles, and middle C, the lowest pitch, had 2 plus cycles for this time duration. You can create your own audible sine waves on page 6 of this section of the site. You may be thinking, okay, so we can get a perfect pitch because sine waves can be produced with an accuracy to a fraction of a hertz, but they just don't sound good to me. Well, that's true. Sine waves are a single frequency and lack the rich harmonics that make musical instruments sound beautiful. However, sine waves are hiding in beautiful instruments, like the flute. You remember back when we were listening to MP3s of instruments on page 7 entitled Trig Tones Within Musical Notes? Well, we were also extracting the data points from those MP3s and plotting them along with the perfect pitch sine wave of the note the musician was playing. Here is the plot for the flute. We can see the flute waveform repeats with the same frequency as the sine wave. The frequency of the sine wave is embedded in the pitch frequency of the flute waveform. There are many more frequencies in the flute. However, all are harmonically related to the pitch frequency. Harmonically related frequencies are multiples of the pitch frequency. In other words, if the pitch frequency was 200 Hz, the higher harmonics would be at 2 times, or 400 Hz, 3 times at 600 Hz, 4 times at 800 Hz, and so on. We know this because if there were any other frequencies, the flute waveform would not repeat at the same fundamental pitch period. The waveform would ooze out of the 2.15 millisecond boundary interval shown and look different from interval to interval. In fact, you can recreate this flute waveform almost exactly with a whole bunch of harmonically related sine functions. But this requires Fourier series, which are covered at the college level.